Cut your Node.js memory usage in half with this one simple trick. Okay, cut the clickbait. This is actually a really cool topic. As I'm sure most of y'all know, JavaScript is not exactly memory efficient. That's why we see hilarious things like Cursor using 3.38 terabytes of RAM. JavaScript's a great language that does a lot of really cool things, but sadly, memory management has never been one of the ones it is strongest with. Which is why I was really excited to see Theo, who is one of the main contributors to Node, come out with a really cool post about how he cut Node memory usage in half with a one-line Docker image swap. To be clear, it's not one line of code changing here. A Docker image swap is a pretty big deal depending on where you're doing it, but the things that led to this performance win are genuinely really fascinating. I feel like most engineers don't appreciate just how much hard engineering work goes into JavaScript because they're quick to dismiss it as JavaScript. But V8 is one of the most complex and impressive projects ever built, and Node is not too far from it. The effort that's going into the C++ that is powering all of this stuff is hard to put into words, and some of it's really cool. I'm constantly surprised by how many hidden flags and features there are inside of V8 and Node that can fundamentally change the performance characteristics. This is one I did not know about that I think is really, really cool. And I can't wait to tell you all about it after a quick word from today's sponsor. If you don't have any users, you can skip this section, but for those who do, it's important to understand what they're actually doing with your service. And that's why today's sponsor is so important to me. Posthog's the only way I like to figure out what my users are doing. I know this looks like an operating system, but they're actually a suite of product tools, things that you need to build real products. The main thing that you're going to use them for is analytics, and they are the best analytics provider. Open source too, but it doesn't really matter because their hosting is absurdly cheap. Their free tier gives you 1 million events, 5,000 session recordings, 1 million requests to feature flags, 1,500 survey results, 100,000 errors and exceptions, and so much more. The data warehouse is one of the coolest parts though, because you can integrate with other services. Integrations like Supabase and Stripe are super useful. Believe me, I spent way too much time in the Stripe dashboard. Posthogs is significantly better, and it's like 2 clicks to set up. I was signing in to show you guys quick, and their vibe is hilarious. The fact that they have a special Valentine's Day little thing is just, that's how they are. Are you kidding? Posthog, I want to just show off the data, and the vibes are immaculate. If you want a data company that doesn't take themselves too seriously, but is a serious contender for managing all of your data, look no further than soydev.link/posthog. So let's dive into how Theo was able to cut Node's memory usage in half, as well as any potential negative side effects of this. V8, the C++ engine under the proverbial hood of JavaScript, includes a feature that many Node developers aren't familiar with. This feature, pointer compression, is a method for using smaller memory references in the JavaScript heap, reducing each pointer from 64 bits to 32 bits. The net is that you wind up using about 50% less memory for the same app without having to change any code. Pretty great, right? Well, almost. Node.js does not enable pointer compression by default for 2 historical reasons. I find this to be really interesting. There's been a couple times where this happened. One of the most famous ones was when I got in the fight with that person who claimed I was lying about performance differences between Vercel and Cloudflare, because when he ran a trigonometry function in a loop, it performed better on Cloudflare than Vercel. The reason for that was actually fucking hilarious. Cloudflare doesn't run Node. Cloudflare runs their own V8-based engine. Vercel runs Node. It turns out there was a flag to do faster trig math that had been enabled by Cloudflare for their runtime of V8 that was not enabled by default in Node runtimes. Cloudflare were the ones who went and found this, fixed it, and got it upstreamed into Node itself, thereby killing the gap there. But that was just like one trigonometry function that didn't have the flag enabled to make it faster. Thanks, Pranch, for that. But yeah, I still can't believe that my shit posting and silly benchmarks ended up making Cloudflare 3 to 10 times faster for various workloads. So cool. And a lot of that just comes down to which flags are enabled and what values are set for them. People don't appreciate how much config there is in Node because none of us ever hit it. Like in TypeScript, you go edit the TS config, but in Node, you don't really config anything. You just tell it to run a JavaScript file. But there are so many flags you can enable in the building and bundling of Node that nobody ever touches. And seeing into them with stuff like this is really fun. So let's see the historical reasons why this particular flag has not been enabled. So going through these reasons, first is the 4 gig cage limitation. which means that enabling pointer compression required the entire node process to share a single 4 gig memory space between the main thread and all the worker threads. This is a significant issue. Cloudflare and Igalia partnered to solve this so that the cage could be per isolate, an individual instance of the V8 engine. To break this down a little bit, for those who aren't as familiar with the worker model in JavaScript and V8, it is possible to spin up relatively safe isolates in V8 that have their own pool of memory. So if I have some work going on in the main thread, like I'm trying to make sure when people hit buttons on the keyboard, something appears as quickly as possible, but I want to do something else that is complex computationally, like generate some UI or run some complex math. If you do that on the main thread, other inputs and other things the user's doing are going to be blocked by that background work. Workers are a way to effectively spin up another instance of the JS engine. It's not really a new instance, it's a sub-isolate within it that has its own memory, its own runner, and can be run in parallel to what you're doing in the main thread so that things happening in the worker don't block the main thread. But in order for that to work, it needs to have its own memory that it's operating against. You cannot share memory between a worker and the main thread. You have to pass events between the two. As a result of this complexity, a lot of people have just never built with workers. I don't really know many JavaScript developers that have used workers in the browser. I'm not talking about Cloudflare workers. I'm talking about browser workers for other threads to prevent blocking main thread as you're doing things. I just don't know many who have used it that way. Cloudflare uses them very heavily. The reason the platform is called Cloudflare Workers is because you don't get your own instance of V8 when you use Cloudflare. The V8 instance has workers spun up for every request. So the same way I could in the browser spin up a worker to do something else while the user is still using the site, Cloudflare has the one main V8 instance with tons of workers that are spun up in order to do these other things so that they can run on the same instance of V8, thereby massively reducing Cloudflare's costs for hosting and also allowing them to be as cheap as they are, relatively speaking. And yes, Naman, web workers are the right term for the version for the web, but what the fuck would we call the ones in Node if that was the case? The point I'm trying to make here is that Cloudflare has invested a lot in doing things to prevent weird memory characteristics in workers because they want this to work as well as possible for the stuff they are hosting. And the problem here was that the entire Node process was sharing a single 4 gig memory space. And whenever a new worker came up, it got to reserve some portion of that because it couldn't reuse the other things. So what's the other problem that prevented this? Some worried that compressing and decompressing pointers on each heap access would introduce performance overhead. And I understand this concern. I actually would have had the same concern that if you have to do something extra, like one more cycle, one more step before you can even access the values in memory, that sounds really bad. And that's why Cloudflare, Igalia, and the Node.js project all collaborated to determine exactly what kind of overhead existed and assess whether it would impact real-world apps. To test this, they created Node Caged, a Node 25 Docker image with pointer compression turned on, because you can't just pass a flag to Node. You can't just be like Node -- compression or something. It has to be built with this on. So they made a custom build of Node 25, put it in Docker so you could easily swap it without having to reinstall Node on your existing instance, and then run production level benchmarks with this on AWS EKS. In short, we achieved 50% memory savings with only a 2 to 4% increase in average latency across real-world workloads and a reduced P99 latency by 7%. For most teams, this trade-off is an easy choice. Fascinating. I would expect this to become the default very, very soon. Let's talk a bit more about how all of this works. First, though, Naman clarified that there are a lot of different types of workers. Cloudflare workers, web workers, service workers, parentheses, Node worker threads, because these are called worker threads, but they are the Node version. Yeah. Super easy to understand. Every JavaScript object is stored in V8's heap. Inside, objects point to each other using 64-bit memory addresses on a 64-bit system. For example, an object like name Alice age 30 has several internal pointers, one to its hidden class, the shape, one to where its properties are stored, and one to the string Alice, which is on the heap. So you might imagine all of these pointers can add up in a typical Node app, taking up a lot of valuable heap space. On a 64-bit system, each pointer uses 8 bytes, even though most V8 heaps are much smaller than the huge address space they could use. For real. Pointer compression takes advantage of this. Instead of saving full 64-bit memory addresses, V8 stores 32-bit offsets, relative distances from a fixed starting point, called the base address. When reading from the heap, which is the section of memory where objects are stored, it rebuilds the full pointer by adding the base and the offset. When writing, it compresses the pointer by subtracting the base from the full address. Interesting. So this is basically just Unix time, but for memory. Seriously, though, it makes a lot of sense. You still have the 64-bit positioning, but if you're only using 4 gigs of memory, you can fit the start to the end in 32 bits. It makes sense to just pick a fixed starting point and work up from there the same way that Unix time does. The trade-off is simple. Each pointer goes from 8 bytes to 4 bytes. For structures with many pointers like objects, arrays, closures, maps, and sets, this can reduce memory consumption by around 50%. Like think about that. For every single key that you have in an object with a value that is something like a string or a sub-object, a pointer is instantiated for all of those. And if you can cut the size of those down by 50%, that's going to be a lot of savings. And then we have the CPU side. Each heap access now needs one extra addition for reads or a subtraction for writes. To put it into perspective, this extra operation is akin to a level 1 cache hit in terms of computational effort. These are incredibly fast operations, and although millions of them are occurring every second, their impact ends up being minimal, akin to a gentle ripple in a vast ocean of processing tasks. And also, to be clear, this additional plus or minus is not happening in the JavaScript world. This is happening in the C++ code that powers all of this. And then we have the heap limit. 32-bit offsets can only reach 4 gigs of memory per V8 isolate, a separate instance of the JavaScript engine with its own memory and execution state. For most node services, which usually use less than a gig, this isn't a problem. Looking at you, cursor. Looking at you. But for everybody else, yeah, that's totally fine. If I see a node service using more than a gig of memory, I just assume it's memory leaking and something is broken, and usually it is. That is a good call. I didn't know this. Apparently, Chrome has had this on since 2020, which would make sense for Chrome for sure, because any tab using more than a gig of RAM is terrifying. More than 4 gigs is just throw the computer off a cliff and start again from scratch. Like, if you have a single tab using 4 gigs of RAM, we've already lost the plot long ago. So Chrome having this on makes a ton of sense. Previously, using this feature required setting a flag at compile time, which often felt like an expert-only option for many devs. Yep, totally agree. As I said before, this is a thing you had to build in, so you had to compile with it. Let's just do a poll. And be honest with your answer, guys. How do you get Node? Comes with my distro, install it with brew-apt, etc. Some type of package manager, download from Node site, or compile from scratch. I have a feeling I know how this one's going to go. Like NVM, I would consider a package manager. I probably should have put that in there. I'm personally on FNM. The point here I'm trying to make is that nobody is compiling Node from scratch. I happen to know that compiling Node from scratch takes a long time. No one would want to do that. Oh, we got our one person who clicked the button. You get the point, though. This is why they introduced Node Caged. The introduction of Node Caged has transformed this, enabling pointer compression with a simple one-line image swap. Again, assuming that you're not doing your own custom Docker image, you can extend the one they provide, but like that's a huge shift. This substantial simplification opens the door for a much broader audience to experiment with the feature more immediately. So here's what changed. Isolate groups. Pointer compression has been part of V8 for years. Node didn't use it before, not because of the CPU overhead, but because of the memory cage limitations. This will be fun, seeing more about how the memory works within Node. V8's pointer compression made every isolate in a process share a single pointer cage, which was a 4 gig block of memory for all compressed pointers. This meant that the main thread and all worker threads had to fit in the same 4 gigs. In Chrome, where each tab has its own process, that was fine. But for Node, where workers share a process, it was a bigger deal. Back in November of 2024, James Snell, who I've seen contributing everything from Cloudflare to Node to many other things, he was one of the ones that came in to help with the chaos I caused with the benchmarks. He initiated this endeavor to address the challenge. I might be misremembering. I thought he was also the creator of Indici, which was a better fetch implementation for Node that became the official fetch implementation for Node. Might not have been him. I'm struggling to find any real information on that. Regardless, James has been involved in a ton of really important things in the JavaScript and Node world. There's a reason he's at Cloudflare, and there's a reason he's the one who proposed this. He knows what he's doing. Cloudflare also sponsored Igalia, Enges, Andy, and Dimitri to introduce new V8 features for this, isolate groups, which give each pointer its own compression cage. So instead of everybody's workers being stuck in the same 4 gig cage, all sharing that, each one can have its own. And this was for V8, to be clear. There's a change in V8 that they wanted because they could do this on Cloudflare to make their isolates better, and also could be used on Node as well. And the C++ change for V8 is simple. Now you can use the isolate new group field. Like you can pass a group to this namespace and it works fine, where previously you wouldn't do that. And that will give each thread its own 4 gig heap. The only limit is the system's available memory. This change, despite being started in November of 2024, took up until October of 2025. 62 lines across 8 files. It took a year for 62 lines to merge. I want to just think about this for a second. This is kind of crazy. And I don't think people appreciate just how hard it is to ship stuff like this. A proposal that Cloudflare needed took a year to go from proposal to shipped. And all it was 62 lines changed that enables the reduction of memory used by Node and other V8 apps by over 50% in many cases. That is insane. that it took that long, but also that they had the wherewithal to push through and make it happen. This is the type of open source work that nobody sees normally that is super important and that I'm really pumped to have happen, but also see publicly here. Shout out to James and Cloudflare for making all of this happen, as well as the people from Megalia who were sponsored on it too. Apparently the pointer compression itself had been broken since Node 22 and they fixed that as part of all of this. Theo tested the changes with a real world Next.js SSR app and confirmed the 50% reduction in heap usage before they approved. So let's see more about these experiments. I'm excited. They made a mock Next.js e-commerce app it was a trading card app with 10,000 cards, 100,000 listings, all the fun things like server-side rendering, search, and a simulated database delay, all on a Kubernetes cluster. They just had 4 setups, all using the same hardware and app code. Standard node, node caged, and then their platform, which is Watt. It's like a similar thing to Cloudflare Workers as far as I understand. It's their open source node application server. These 4 tests. Let's see what the usage looked like. They had a bunch of mock traffic. 20% was homepage, which was SSR'd. 25% was search. 20% was card details. 15% game category pages, yada, yada. Let's see what the results look like. For a plain node, average latency went from 39.7 milliseconds to 40.7 milliseconds, which is a bump. That's 2.5%. The P90 got meaningfully worse, from 78 to 82%. That's a 5% bump. So 5% slower for the 10% slowest stuff. But much crazier is the 7.8% faster for P99. So the top 1% slowest got way faster. The top 10% slowest got slightly slower. Everything else was pretty close. Fascinating. A smaller heap means the garbage collector has less work to do, so there's fewer and shorter garbage collection pauses. That's a really good point. If you're not familiar, since JavaScript doesn't have you manually creating and freeing memory, the V8 engine has to handle that for you. When it detects that values are no longer being used or tracked, it will find them and go clean them up eventually. But it has to choose to go do that, and it's not going to block your stuff for the most part. But when it is time to clean up that stuff, that's called garbage collection. And the garbage collection process will block things when it's happening. When GC is going on, other things can't be. And it's not going to take a super long time, but it will take actual time. And that's what the P99 is hitting. 99% of requests don't get blocked by garbage collection, but the 1% that do now can have the collection happen much faster, which is a huge win. So how did this work in their runtime? It actually looks like it was worse for average P90 and P99. The P99 went up a ton, but the max, which is beyond P99, it's like literally the worst case on each, was down 20%. Fascinating. I'm guessing they're just having garbage collection happen less, so they're not getting the same benefit initially. I wish they would acknowledge this plus 18.1. I'm so curious about that. If you compare standard node with Watt, which is their runtime, plus the pointer compression stuff, the gap is pretty meaningful. The P99 is 42% faster on their thing. Seems cool. I should definitely look into Watt more. Apparently, they had published benchmarks before that were not looking good. It showed a 56% overhead when they enabled this. And that was a simple Hello World Next.js starter app. A simple Hello World SSR page mostly does V8 internal work, compiling templates, diffing the virtual DOM, and joining strings. There's no I/O, no data loading, and no real app logic. Every operation goes through pointer decompression. Real apps are different. Typical request spends most of its time on things like I/O wait, data marshalling, framework overhead like routing, middleware chains, header processing, and then OS and network stuff like scheduling with TCP, TLS, all those things. I agree for the most part. I've tried to push this a lot with people. If you're running a script that just curls an HTML page being generated by React, probably not the best benchmark. There's a ton of other things that matter. I still think that a 56% decrease in performance on a thing that doesn't do all this work is really bad, and I want more info on that case. Hopefully we get more of that here. I like this framing. As the ratio of real work to pure V8 pointer chasing increases, the overhead of pointer compression shrinks proportionally. Our e-commerce app includes simulated database delays of 1 to 5 milliseconds, JSON parsing of datasets with 10,000 plus records, search filtering, pagination, and full SSR rendering with React. In that context, the pointer decompression overheads round to noise. Yes. Takeaway being that you should always use realistic workloads for benchmarking. Yeah, I tried this myself when I was getting in all of the fights about running a fucking trig function in a loop. I am proud. I feel like I had some very small but meaningful impact on this with the benchmarks I did in the past, getting Cloudflare to like kick up their focus on performance stuff. I'm proud of the impact I may or may not have had here, and I'm just pumped to see it all shipping, honestly. And to be clear, the impact I had was not I did something great, it's that I made something stupid and that turned into other people making something great, which is really cool. There's a very fun deep dive here about how the garbage collection stuff works, which I'm excited to read through. There are several types of garbage collection within V8, and these are the two that matter primarily. There's the minor GC, which is scavenge. It will copy a live object from the young generation. Time is proportional to the number of live objects and their size. So this is, as I understand it, when a new object is generated, it needs to be put somewhere. So a tiny bit of garbage collection will be done just to figure out what space is available so I can drop it in wherever that fits. And then we have the major GC, the mark, sweep, compact. This is the thing that actually goes through everything in memory, identifies all of the reachable objects, sweeps the dead ones, and then optionally compacts. The time for this depends on the total heap size and level of fragmentation. To quickly simplify what this is saying, you have a bunch of stuff in memory. Things point from one thing to another. If there's nothing pointing to an object anymore, it doesn't need to be held in memory anymore, and it can be disposed of. There's a lot of edges where V8 isn't necessarily able to perfectly know if the thing is still relevant or not. I did a video about weird V8 quirks forever ago that I dove in on all this with. The way this works is going through, finding anything that doesn't have things pointing at it, and then cleaning that up. But it has to go through everything in memory to do this, so it takes actual time. We're talking milliseconds, but a number of milliseconds. It means something. It's also worth noting that garbage collection is a much bigger issue in languages that are, I'll be real, faster. Like managing your own memory in JavaScript wouldn't make much sense because the runtime is still going to be the major bottleneck. Whereas in something like Go, the garbage collection is the only thing that is slow. So it will often end up becoming a blocker in certain scenarios. That's why companies like Discord are moving some of their backend stuff off of Go to Rust. Even though Go is just as fast as Rust for most things, the fact that the garbage collection can make some requests slower caused unreliable traffic patterns. Like if it does garbage collection when you're making a request, your traffic takes longer than it does for other people. That's why they moved to Rust, because they wanted to reduce the amount of times that garbage collection would interfere with real traffic. Dancing around garbage collection is an art, and I'm so thankful that us in the JavaScript world don't have to do it ourselves, that the much smarter people building Node and V8 for us have solved so many of these things. But yeah, the major GC is the thing that matters here for the numbers. And if the size of the pointers is half of the size, you end up having way less data to deal with when you go do the garbage collection. Because of the pointer compression, every object is smaller. This is domino effects. Things like the objects fit in fewer cache lines. Because the compressed object that fits in a single 64-byte cache instead of 2, that makes garbage collection much easier. If a piece of data takes up twice as many slots that you have to check twice as much shit when you do the garbage collection. More importantly, though, the young generation, which is their primary, like these are things that were recently instantiated that we probably want to keep in like immediate memory, that will fill more slowly because smaller objects are taking up less space. The major GC has less to scan. A 1 gig heap with compressed pointers contains the same logical data as a 2 gig heap without, so the scan actually takes less time, of course. And the compaction is moving things around less, because when you do the compaction, you're taking the things that are gone and flattening to the front. I guess we do need Excalibur after all. If we have our memory, and in our memory, we have stuff. Like let's say we have object 1, object 2. Object 2 is actually quite big. Object 3, and then we'll round this out with object 4. And now we have this new object, object 5, and we want to instantiate this and put this into memory. There's a problem though. There's no fucking space. So this triggers a garbage collection. Let's say object 1 points to 3, object 3 points to 4, and nothing's pointing to 2. What ends up happening with the garbage collection pass, 2 gets deleted, and then these get moved. You might be questioning why move the things. Well, I'll show you. Let's say it was actually like this. We had object 3, object 1, object 4, and we have this space between the two. But this object is too big to fit in either of those spaces. This is called fragmentation. So the reason that we move everything is the same reason we defrag our drives. It's so all of the free space is at the end, so it's easier to add in new shit without having to unfurl it and break it out across so many things. It's also why virtualizing memory is so valuable, because if the OS can handle the fragmentation part and you're just dropping pointers directly to things that aren't real but are in your space, is great. And obviously you can understand why things being half the size means less movement has to happen, thereby this process ends up being cheaper and faster. And as Theo says here, the end result is that GC pauses are both shorter and less frequent. This corresponds to what we saw in the P99 and max latency numbers. When a long tail request lines up with a GC pause, the pause is now shorter. They drop some fun cost numbers here too, which are Very interesting. If your current node on Kubernetes takes 2 gigs of memory per pod, this compression can knock you down to 1 gig. You get the same app and performance, but can run twice as many pods per node or use half as many nodes. What would having pod memory do to your bill? Take a moment to calculate the potential savings based on your current setup. For them, this example was based on a 6-node M5 2x large, which is at 38 cents per hour, roughly. That's about $16,600 a year. If you can go from 6 nodes to 3, because you need half as much RAM, you're saving $8,300 a year. If you have a real production fleet with 50 or more of these nodes, the savings could be between $80,000 and $100,000 a year without changing any code. That's pretty huge. You know what would actually benefit a lot from this? OpenClaw. Someone should make an OpenClaw Docker image based on this one, because that compression is going to help it a ton. You'll be able to run OpenClaw on way smaller boxes as a result of this. Like, genuinely, that's really cool. This also means you can double your tenant density. Multi-tenant SaaS platforms where each tenant runs in their own isolated node process often will hit memory limits as the binding constraint for density. Yeah, absolutely agree. If you have 5 customers and all of them are running on the same box and each one needs 2 gigs of memory, even if they're not doing processing all the time, like you're not bottlenecked on CPU, you're bottlenecked on RAM. If you can cut the amount of RAM each of those instances needs by half, you can put twice as many things on that box. That's a big deal for a lot of memory constrained work, which is a lot of these like multi-runner cases. This also will help unlock edge deployments. I didn't even thought of that. That's a big deal. If you don't need as much RAM, you are much less blocked when you try to deploy things at edge. Lambda at Edge, Cloudflare Workers, and Dino Deploy have strict memory limits between 128 megs to 512 megs. The reason Cloudflare sponsored this work is because the worker runtime needed pointer compression to support more isolates. Yeah, they can now put twice as many things in when they're not using CPU. That's crazy. In a world where 128 gigs of server RAM is $2,500, this means a lot. Yeah, I should have thought about that before. The fact that RAM is so expensive makes this a really, really good, well-timed change. This is another one I hadn't thought of. For WebSocket apps, you often end up blocked on memory because if you're maintaining all of these connections and don't have anything to send yet, you're not using much CPU, but you are using a shitload of RAM because each of those connections is conservatively taking 10 kilobytes per connection on the heap. That puts you at 500 megabytes of RAM with 50,000 connections on one box. Now you're down to 250 meg. That's huge. So you can have 100,000 connections on the server that could previously only do 50,000. Huge. Like if some random service was promising me this, I wouldn't believe them. But this is Theo Kalina, who is my go-to reference point for things going on in Node. One of the best C++ engineers I've ever met. Theo is really good. He is writing this as a maintainer of Node, not as a person trying to sell you something. So I do believe him fully with this. They do call out the fact that if you do actually need more than 4 gigs of RAM per isolate, then this doesn't work. This is not going to help. This is probably going to cause problems. It's not an option. But only the V8.js heap is what's living inside the cage. Native add-on allocations and array buffer do not count against that limit. That's good to know. Like, I don't think any of the apps using that much RAM aren't offloading things like that, so almost certainly good. But there's one more compatibility constraint. Native add-ons built with the legacy NAN, the native abstractions for Node, won't work with pointer compression enabled. NAN exposes V8 internals directly, and pointer compression changes the internal representation of those objects. When you recompile, the ABI is different. Add-ons built on the Node API, which was formerly an API, are unaffected because Node abstracts away those pointer layers. Apparently, the most popular packages have all long since migrated. Sharp, bcrypt, Canvas, SQLite 3, Level Down, Buffer Util, UTF-8 Validate, all are good. Apparently, NodeGit is one of the few things that is still using NAN. If you run npm ls nan, if nothing shows up, you're good. This will actually be fun. Let's try that. Find a T3 chat code base. Woo! T3 chat is clear. We can turn this on. That's actually really exciting. Our memory usage is not great. That'll be a huge win. So if you can run this command and nothing happens and you're deploying your Node apps via Docker, I'm with him. You absolutely should try this. There isn't much to lose. I'm going to try turning this on for a few things that I'm working on right now. I'm actually really curious how this goes. Also, how it performs compared to Bun. This was a phenomenal article. Thank you, Theo, for writing this. This is a super cool deep dive. I hope that y'all learned something as I read this. And if you haven't, go give Theo a follow. He's putting so much work in for all of this and is not compensated fairly for it. I can promise you guys that much. He's one of those quiet people behind the scenes keeping the internet functioning as we know it. Give him a follow, support him for the work he does. I appreciate him immensely, and I hope you guys do too. Are you guys as excited as I am about using less RAM, or do you just want to save money now that it's all so expensive? Let me know how you feel in the comments, and until next time, peace nerds.